Thank you so much. Thank you very much for the invitation. I'm very happy to be here speaking with all of you. Before I begin, about maybe 12, 13, 14 months ago, I made a decision that every seminar talk I gave, I would begin by advertising a petition that I hope people will consider joining. Um, I'm going to put the link in the chat. This is a boycott campaign organized by a group that I am a part of and focused on the BDS campaign targeting Israeli academia for its complicity in the ongoing genocide in Palestine. Um, there are other such campaigns floating around in mathematics. There was a big French letter that circulated recently. This is a letter that was organized by Americans and we feel has special significance given the role that the US is playing in um, perpetuating this violence. And it is open to all mathematicians, any country, any nationality. So we would really love if you could either consider signing on and or passing it along to anybody else you know. Happy also to address questions about that. If you want to send me an email, I'm very easy to find on the internet. You can always reach out. Can I just make sure before I begin the mathematics that I'm audible? Can you hear me well?
Yeah, yeah, yeah.
Okay, great. Okay, so today I want to tell you about a problem. It's a problem in dynamics, and it has to do with the following kinds of objects. So the sort of central object that we'll study today are metric graphs. So and what is a metric graph? A metric graph is just a one complex. So you may have some number of vertices, and then you have some cells connecting those vertices in some fashion. Okay, I don't know. You're also allowed to have multiple edges connecting the same two vertices, and you're also allowed to you maybe you have three or four, who knows? You're also allowed to have edges that start and end at the same vertex. This is allowed. We will also make the requirement that every vertex is adjacent to at least three edges. So, for example, this situation here, let me get my laser. This situation here won't occur for us because there's really no distinction that's uh, important between a single edge that is subdivided in two versus two edges that have a vertex in the middle. And so uh, you may as well think of this situation here as just being one edge that just happens to be bent. And for this reason, all of our vertices will have a valence of at least three. So maybe this is what the graph looks like. Now this is allowed. Now, a metric graph is a graph where you assign every edge a positive number, which is meant to be the length of that interval. So, who knows? This is pi, this is 2, this is 7. You can make this randomly, it doesn't matter. 2.3, whatever. So, every edge has a positive weight. And now, once you've assigned every edge a positive weight, this becomes a metric space just using a path metric. So the distance between any two points, where the points here may be vertices and may not be vertices, maybe this is x and this is y here, is just as one always does in this situation. You just define it to be the infemal um, arc length of any path in, let's call this G, from X to Y, and the arc length of a path is defined in terms of the edges that the path traverses. So you can, for instance, if X is here and Y is here, and the length of this edge here is 2.3, then if I want to go from X to Y, here's a path from X to Y. Now, what is the length of this path? I just measure the total. Let's see. Why did I say this? Um, uh, I forgot to say one thing, which is that every edge here, um, let's say this way, every um, interior point of an edge can be located in terms of the fraction of the edge that occurs on either side. So this is also part of the data of a metric graph. So in other words, given this point x right here, I also know that this point x is maybe you know uh, two-thirds of the way to y and one-third of the way to whatever this point is. And for this reason, I can um, determine the length of this by just taking 2.3 and multiplying it by two-thirds. This is sort of a side point that doesn't really matter because in the context of the problems we're going to consider, we're really only going to care about the distance between various vertices. But in any case, it is possible to define the distance between an interior point of an edge and a vertex. It just very infrequently comes up. So these are the kinds of objects that we're going to study. And what we're mostly interested in is the following function. Okay. So given this object, I'm going to define a function ng. This is a function from, let's say, the reals to the naturals. And what does it do? So if I plug in some, in fact, it's only positive reals. If I plug in some positive real number, then the output of this function is going to be just the size of the number of cycles on the graph G with total length at most the input of the function. So if we have an example here, maybe our graph looks like this. And maybe just for simplicity, let's assume that every one of these edges has length 1. Okay. So in this situation, here's an example. And by the way, there's a word here that I should have put in. It's not just cycles, it's what are called reduced cycles. And I will explain what that word means in the following example. So what we could imagine here is what if we tried to compute ng of 1/2? This is asking for the number of cycles on this graph with total length 1/2. Okay, well, let's think. So first of all, here's a cycle of length 1/2. I could start at this vertex, go over 1/4, and then just come back 1/4, totally retracing this interval of length 1/4. And that's technically a cycle. A cycle just means it's a path that starts where it ends. However, that's where this word becomes crucial. So a reduced cycle is a cycle which never backtracks along any edge. And so we wouldn't count that because it's not reduced. So it's not too hard to convince yourself that the number of reduced cycles of length at most one half on this graph is zero. There are no reduced cycles of length one half or less. The smallest cycle you can have, which is reduced, is for instance, this is one, but it has length one. This is another one, but it has length one. There's many more. Here's one. This reduced cycle has length two. This reduced cycle has length three. Okay. This reduced cycle has length, let's see, one, two, three, four. That's a reduced cycle. So in a reduced cycle, you're very welcome to traverse an edge in opposite directions. For example, we just did that in the example we just saw, right? We went this way first and then around this and then the reverse direction and then around this. That's fine as long as you do not traverse an edge in opposite directions immediately after each other, because if you do this, it's not reduced. Okay. So the basic question that one might ask about this function is um, how how does this function grow? And there's a number of ways to think about this. But I mean, I think maybe probably one of the easiest ways to think about this is we can think about it in terms of universal covers. So any one of these objects that we've drawn is universally covered by some tree, right? So there's some infinite tree. I have no idea what it looks like that covers our graph, okay? And it goes on forever. And every single one of these edges is assigned a weight in accordance with whichever edge it lies above under this covering map. So, for example, in this picture, um, I don't know, like uh, maybe like this is a green edge and it's covered by this edge and it's covered by this edge and it's covered by this edge and so on and so forth. And so if this green edge has weight pi downstairs, then it induces a weighting of pi on every single green edge upstairs and so on and so forth. So in this fashion, the universal cover becomes a metric graph. Okay. And now uh, it's not maybe too hard to convince yourself. So basic, I'll just say observation. When L is very large, almost every cycle, almost every cycle of length at most L goes over every vertex and edge. So in other words, if we go back to this example here and we set L equal to 1 million, then the number of cycles of length at most 1 million that avoid this. They do not go over this particular loop. Well, if you don't go over this particular loop, that means the only two edges you have access to are this edge and this edge. And if you're reduced and you only have access to this edge and this edge, in fact, you only have access to this edge, if you think about it. Because if I ever use this edge at all, well, there's only a couple of ways it could happen. Maybe I go here, here, because I'm not going over this loop. Whoops. Oh, that's not good. I just accidentally pressed a button on my tablet and stopped sharing. Let me just reshare. Sorry about that. Where is the share button? No, I lost it. I'm still sharing my screen. That's why I can't find it. I just exited out of the program, my notes program. Here we go. Okay. So, as I was saying, if you're not allowed to use this loop, then maybe the cycle starts here and then comes back here. But now my only option is to go this way again, and that's not reduced. Or perhaps the cycle starts at this vertex, and maybe I go like this. If I try to go over this again, I have no choice but to go backwards now, and I'm not reduced. So the actually I only have access to this small piece, and there's just not that many cycles that only choose this loop when the length is huge. It's way more advantageous to use the entire graph. So what this observation says is that we can more or less ignore the cycles that avoid a piece of the graph. If we're interested in counting all of the cycles, at least asymptotics, the growth of this function, we can more or less just restrict our attention to every cycle that not only has length at most L, but which goes over our favorite vertex. Because the only cycles that avoid that vertex, there's going to be very few of them in comparison to the total number of cycles. So I can pick my favorite vertex. Let's say I pick this vertex here, and I only want to look at the cycles that go over that vertex. Well, I can take this red vertex and lift it to the universal cover. Maybe here's one, here's one, here's one, and so on and so forth. There's infinitely many of these red um, points in the universal cover, but I'm just going to pick one. So let me just pick one of the pre-images of this red point. And now just basic topology tells us that if I have a cycle, again, I did it. I keep touching that point on the screen. Let me move it over there so I don't touch it again. Sorry about that. Okay. Back to this picture. If I have a cycle of some particular length starting at that red point, then it corresponds via a path lift to some path in the universal cover between two different red points. So maybe again, this point here is red. Okay. And so this NGL function, we can reinterpret it as actually being a sort of lattice point counting problem in the universal cover. It's just equal to the number of red points in this tree within the ball of radius L around the base point, which is the point colored red in the middle of the picture. And so this maybe gives us a clue as to how to estimate the growth of this function n sub g. We have a tree here. The assumptions that we've made about our metric graph, namely that every vertex has valence at least three, implies that the tree, which universally covers our graph, will also have the same property of at least three edges around each vertex, and that's going to imply that the growth of red points, which are not all the points, right? Some of the points are not red in this tree. However, a definite proportion of the points in this tree are red. And the number of points inside of a tree as you let the radius grow, that's an exponential function in the radius of the ball. And so this sort of very basic analysis suggests that NGL should grow something like exponentially in L. Okay. So it turns out that here's a theorem. This is very classical material. So this I don't even know who to credit this theorem to, but it's, at this stage, many decades old. The limit as L goes to infinity of what I get when I take NGL, I take the logarithm and I divide it by L exists. So one way to heuristically think about this theorem is so heuristically, this is saying that NGL looks like e to the KL for some k, which I don't know what the k is. But when I take the logarithm of this, I get KL, and I divide by L, I just get the k. Okay. So this limit is called the entropy. And for reasons I don't fully understand, in the literature, the letter H is often used for entropy of the metric graph. Okay. Some people also call it the volume entropy because it's related to the volume growth of this universal cover, as we just observed. Okay, so let's maybe explore some extremely basic facts about the entropy that will be helpful in navigating some of the deeper results we'll talk about later. So here's a basic lemma about entropy. Before I state it, let me just say, let me give you a new piece of notation. So denote by lambda times g. This is just some scalar. The metric graph one obtains from G by scaling every weight by lambda. Obtained from G by multiplying all edge weights by lambda. Okay. Then, if I want to compute the entropy of this new graph, it's related to the entropy of the old graph if I divide by lambda. Okay, so this is, I think, intuitively clear. We should prove it. The proof is one line. But before we prove it, let's just at least do a sanity check and ensure that we're understanding why the relationship should be reciprocal. So imagine lambda is 1 trillion, a huge number. Then what you've done is you have taken every edge of the graph G and stretched it by a huge amount. And so in this fashion, you have guaranteed that there are way fewer cycles under any given length because now any cycle that used to have length 20 now has length 20 million. And so there maybe are no more cycles of length 20. And for this reason, the entropy of the new graph should be divided by the scalar, not multiplied by it. That's just the intuitive idea, but let's just prove it. It's very short. The proof of this is, well, okay, by definition, this quantity is, let's just write it down, the limit as L goes to infinity of just literally the definition, lambda GL with a logarithm here divided by L, okay? And now we just make the observation that if a cycle has length at most lambda uh, times, sorry, if a cycle has length at most L on the graph lambda times G, then its length on G is at most L divided by lambda. So I can rewrite this limit as the log of NG L over lambda divided by L. And now we'll just do a simple change of variable. So let's set, I don't know, t or something equal to L over lambda. And if I do that, then I can rewrite this as the limit as t goes to infinity of the log of n gt. L is lambda times t. So this is what I obtain. And then I just notice that this, if I ignore the lambda, is precisely the entropy of G. So that's the entire result. That's the proof. Okay. So that's a very basic fact that can be useful for us. Okay. Now, maybe it's actually time to state the question that we being myself, Taufik Ahmed from Berzait, and Matt Clay from the University of Arkansas, were interested in answering. So, central question of this talk. So, given such a G, I'll define this word in a minute, with rank at least three. The question is, does there exist a proper, maybe I'll just write it in full words, just to be totally clear. Does there exist a proper subgraph? Sorry, I forgot again, of course, I always forget this. Given such a G with entropy equal to 1 and rank bigger than or equal to 3, does there exist a proper subgraph? Let's call it H. Um, does there exist? This is very sloppy. I'm putting my quantifiers all in the wrong place. Does there exist a, um, let's say, lambda, um, which depends only on the rank of G, and a proper subgraph H, so that the entropy of H is at least lambda? Now I owe you very many things now because I just wrote this question down. It makes no sense without first knowing what the words mean, and then second, without understanding the motivation for this question. So first of all, what is this word here? Okay, well, every metric graph is homotopy equivalent to some rows. Okay, so this just means um, the number of self loops in the rows you obtain by contracting a spanning tree. Okay, so I don't know people's um, mathematical backgrounds. So let me just do a very quick example here. Like, okay, here's an example. This is what my original graph looks like. A spanning tree in this graph would be, here's a spanning tree. A spanning tree is just a tree in the graph that sees every vertex. In this case, it consists of just these two blue edges. And if I contract these two blue edges, I can do them one at a time. If I contract first one of these blue edges, maybe um, I would get this. Okay. And then if I do the final blue edge, I would get this. Okay. And so what we see is that the rank, therefore, of this graph is 4. Okay. So I'm only interested for reasons that I will explain to you in graphs of rank at least 3. Okay, let me explain this assumption here. Why do we care about the entropy being 1? Well, the lemma that we just proved before we stated the central question tells us that um, every metric graph, no matter what its entropy is, as long as its entropy is not 0, any metric graph with positive entropy is projectively equivalent to a metric graph with entropy 1. Because if the entropy of a given graph is 17, I can just take every edge and multiply it by the scalar 17 and obtain a new metric graph whose entropy is 1. And I don't really think of the new metric graph and the old metric graph as being intrinsically different, right? Because all I've done to obtain the new from the old is to multiply every edge by the same number. So the shape of the graph is exactly the same. So this uh, assumption of entropy being 1 is just a way to um, like normalize everything projectively. Okay. So that's not too crucial of an assumption. Now, before I tell you why this question is interesting, let me convince you that it's hard. Okay, I don't know. I think a worthy question in mathematics needs to be both hard and interesting. So first I'll tell you why it's hard, then I'll tell you why it's interesting. Why is this question hard? This question is hard precisely because of we go all the way up here and remember this observation. When L gets very large, you should expect almost every cycle to go over every single edge and every single vertex of your graph. And so, if you are only allowing yourself the freedom of a proper subgraph, any proper subgraph, even if you choose a proper subgraph that misses only one edge, is not going to see almost all of the cycles in the sense that every single cycle will at some, not every single cycle, 100% of the cycles, I'll say it like that. The proportion of the cycles which do not live on that proper subgraph goes to 1 as the length of the cycles goes to infinity. And so trying to find a proper subgraph that contains a definite exponential number of cycles is difficult. And so that's, I think, why this is a challenging question. I haven't yet, even though I still have to tell you why this question is interesting. I don't think I've fully convinced you that this question is hard yet, because I didn't justify why rank three or above. Well, this is not so hard to understand. It's a necessary assumption. If I consider graphs of rank 2, then the answer is obvious and the answer is no. So here's a very simple example. Okay, here's a rank 2 graph. Okay, I don't care what the weights are. Pick them whatever you want. Row 1, or I'll say W for weight. Okay, doesn't matter. There's only one proper there's two different proper subgraphs I can choose. There's this one or there's this one. That's it. And they both have entropy 0. Why? Because if I take for let me call this subgraph here. This is H1 and this is H2. Okay. Well, what is NH1 of L? This is the function that computes cycles on just the left half of this graph with length at most L. But it's not hard to see that the number of cycles on this is exactly equal to what is it? Like, not exactly, but I mean, probably there's like this is supposed to be a whole number, so maybe there's a floor or a ceiling function I have to put in. So I'll just do this. It's basically 2 times W1. No, it's not that. It's 2 times uh, L divided by W1. That's right. So in other words, like, what are the cycles I can have? All I can do is go, I can choose to go counterclockwise as many times as I can before I run out of length. And how many times can I do that? I can do that exactly L divided by W1 times before I run out. But I can also, of course, do this clockwise. And again, I have L divided by W1, and that accounts for the 2. Okay. So if this is the correct I mean, asymptotics of NH1 of L, then we can immediately see that the entropy is just going to be, we must take the log of this function and divide it by L and take a limit as L goes to infinity. I mean, this function grows linearly. This function grows linearly in L, not exponentially. And so when you take the entropy, you just get 0. And this is not anything special to do with this graph. I mean, no matter which rank 2 graph you choose, there's only, first of all, two kinds or something of rank 2 graphs under our assumptions. You could have there's three, right? There's the rows, there's what's called the theta graph because it looks like the Greek letter theta, and then there's the barbell graph. Those are the only possibilities in rank 2, and you can run this exact same argument in each of these three cases, no matter what the weights are of the edges. The entropy is always going to be 1 whenever you throw out even one edge. Entropy is always going to be 0, excuse me, whenever you throw out even one edge. And so there's never going to be a an interesting lower bound on the entropy for any subgraph in that case. And that's why rank 3 is a necessary assumption. So I think like what I hope I've done in this time is introduced you to the central objects of study, which are the metric graphs. I've introduced you to this entropy function. I've given you like a very basic lemma, and I've given you the central question. And I hope I've also convinced you that the central question is difficult. But I haven't convinced you at all that the central question is interesting or motivated by other kinds of mathematics at all. And so that I can do in the second part.